Hello, I'm Marco, CEO at Simulics. In this video I will show you how embedded software developers can use the new interval search feature of our reverse debugger to track down non-deterministic software faults very easily. What we see here is the MPLabX IDE version 3.45 with our reverse debugger plugin for PIC24 installed. It shows up the display of the PIC24 starter kit, the timeline, program memory, and the registers. When I hit the Debug Project button, we see a Game of Life demo running. Actually, it's two Game of Life tasks inside a FreeRTOS environment that performs preemptive scheduling via timer and interrupts. We do observe some pixel artifacts, probably a software fault, and after some time, the whole display appears to scroll down some lines. This is not what we have programmed, or at least not what we intended to. So, how can we find out what the problem is? As for the pixel artifacts, we could set a breakpoint at a putPixel function, and that's also what we probably would do in the conventional debugging workflow. But thousands of pixels have been put correctly before the first glitch happens, so this will certainly not bring us any closer to the bug. It looks like this will become a long and tedious debugging session, especially when we presume this is a non-deterministic behavior. But things get simple when our reverse debugger comes into play. We can just click and jump around in the timeline, which is a representation of the target's runtime. The red cursor shows our current position in time. We can now go back and forth, inspect the program state that was at the time and decide whether a software fault did happen or not. If the fault is present at our current position in time, we know that it must have happened somewhere between the beginning and now. Otherwise, we know that it must have happened somewhere in between now and the end of the run. In our case, the fault is the unexpected display scroll down. We do accordingly either expand the left or the right part of the window with one of these two buttons at the bottom. Now we find a zoomed-in representation of the range at the bottom of the window, which allows us a more fine-grained positioning of the cursor in the target runtime. To track down the fault, we proceed with this until only a few instructions are left. By default, the cursor gets repositioned in the middle of the range to save us clicks, and we only need to click the buttons. This is just like a binary search, but we also can move the slider manually if we want. Now we have only 21 instructions left, so let's just pick up the one that causes the fault. Okay, it's this one. It writes data to the parallel master port which the display is connected to. Let's go back a bit further. We are inside a putPixel function. Let's go back further. Now we are in the handler routine for the timer, which did execute the FreeRTOS scheduler. Let's investigate further back in time. We have added reverse versions for the run, step into, step over and step out button. Go back a bit further, and here we are in the scheduler. This means the FreeRTOS scheduler has interrupted one of both tasks while it was still in the middle of a putPixel function. This is critical because putPixel requires several data values to be written to the display, one after each other. This must happen atomically, otherwise the state of the display gets corrupted. So what do we need to do? Exactly. We must protect the putPixel calls and the function that draws the Game of Life screen with a mutex. Having done this, we see that no more glitches occur on the display. This is how the debugging workflow with our tool looks like, how it simplifies embedded software debugging and helps analyzing and fixing bugs, even in the case of non-deterministic program behavior. For more information, or to download the trial version of our reverse debugger, visit us at Simulics.com.